Hello and welcome to yet another lecture on Basic Electrical Engineering, paper code ESEE101. Myself, Prathita Roy, Assistant Professor of Dr. Sudhir Chandra Institute of Technology and Sports Complex, Department of Electrical Engineering. Today, my topic is speed control of separately excited DC motor. Lesson objective. After the end of this topic, students will be able to understand the concept of speed control of separately excited DC motor. So we are starting with speed control of DC motors. So, the speed of a DC motor is given by the relation that is speed A equal to V minus IA RA by K phi. The speed is dependent upon the supply voltage V, armature resistance RA, and the field flux phi, which is reduced by the field current. Thus, there are two general methods of speed control of DC motors are variation of resistance in the armature circuit. This method is called armature resistance method. Variation of resistance in armature circuit, and another is called variation of field flux. This method is called field resistance control. The variation of field flux. This is called field resistance control. So first we will start with armature resistance control. So in this method, a variable resistance. This is the speed control of a DC shunt motor by armature resistance control. And here is the speed control of a DC series motor by armature resistance control. So what is the process of armature resistance control? That in this method, a variable series resistors, that is called RE, this one, same for this one, that is connected in series with the armature circuit, that is connected in series with the armature resistance, both for the shunt and the series motor. And this method that of connection for a shunt and series is shown in this figure that we have seen. The field that is directly connected across the supply, the field, it is directly connected across the supply. Therefore, the flux phi is not affected by the variation of RE. So the figure that shows that the method to connect an external resistance, that is this figure, is RE in the armature circuit of a DC series motor. So in this both figure, we will obtain the speed current characteristics for both shunt and series motor. So the both of the figures that shows the typical speed current characteristics for shunt and the series motor. In both the cases, the motor that runs at a lower speed as the value of RE is increased. RE that carries the full load armature current. Hence, RE should be designed to carry continuously the full load armature current. The main disadvantages of the armature controls are: the first one is a large amount of power that is wasted in the external resistance RE. Speed control is limited to the speed that is below the rated, and increase of the speed is not possible by this method. For a given value of the external resistance, the speed reduction is not constant but varies with the motor load. This method can only be used for small DC motors. So, if a RE is added in series with the armature, which is cause the motor to run below the normal speed. This is the speed current characteristics for the shunt motor. This is the normal value of the speed when a series resistor is connected. This is the graph for the speed versus armature current with series resistor. So this is the another speed armature current characteristics of this series motor, and with the additional series resistor it is clearly seen that the speed is decreased. So another is process is called the variation of field flux, that is phi. So the speed control of a DC shunt motor by field flux control. The flux of the DC motor that is being produced by the field current, control of the speed possible by field current variation. In the shunt motor, the field current control is achieved by connecting a variable resistor, that is RC, in series with the shunt field winding. Connecting a variable resistance RC in series with the shunt field RSH. So the resistor that is RC is called as shunt field regulator. So the connection of the RC in the in the field that is reduce the field current in which that reduce the field current, which in turn reduce the flux. The reduction in flux will result in increase in speed, at speed is inversely proportional to flux. So this method of speed control is used to give motor speed is above the normal speed. The variation of field current in a series motor is done by any one of the following two methods. One is called the speed control of DC series motor by using diverter in field circuit, that is RD. So a variable resistance, that is RD, is connected in parallel with the series field winding RSE, that is clearly seen. So the parallel resistor is called the diverter. This is called the diverter. portion of the main current, a portion of the main current that is diverted through the RD. As a result, the reduced amount of current will be flowing through the RD. You see? So as a result, the field current goes decrease, the field flux goes decrease, and the speed will increase. This is the general process of speed control of DC series motor by using diverter in the field circuit. So another is the field control, speed control of DC series motor by using the diverter in the field circuit. And another is the speed control of DC motor by using tapped field control. So the second method is use a tapped field control, a tapped field that it is shown. Here the ampere turns that are varied by varying the number of field turns. This arrangement is generally used in electric traction, where the number of ampere turns are varied by varying the number of field turns. So this is the graph that for the shunt and the series motor that we have seen. So as the RC is going on increasing, the speed also increase, and as the RD goes on decreasing, the speed and the torque characteristics for the DC series motor is also seen here. So it is clearly seen that the advantage of field control are that this method is easy and convenient, and since the shunt field I of SH is very small, the power loss in the shunt field is also small. So let us take an example in order to understand this process. So an example that says that a shunt wound motor with an armature resistance of 0.2 ohm is connected across a 400 volt supply. The armature current is 40 ampere and the speed of the motor is 100 rpm. Calculate the additional resistance which should be connected in series with the armature to reduce its speed to 700 rpm. Assume the armature current that is remain same. So in order to approach this problem, we have to find the additional resistance that is connected in series with the armature to reduce the speed to 700 rpm. We have to find the value of the armature resistance. So let us RA, this is the additional armature resistance. So the RA value is 0.02 that is given. V is 400, IA is the 40 ampere, and EV is the 1000 rpm. So the additional resistance that is connected in series with the additional resistance is R. We have to find the value of this R. So we have to find the value of this R. So before the additional resistance connected, the value of EB1 is V minus IAR. That is 400 minus 40 into 0.2, that is 392 volt. EB2 equals to V minus IAR plus R, that is 400 minus 40 into 0.2 plus R. So for the shunt motor, the phi is constant, so EB is directly proportional to the speed. So we can write EB1 by EB2 equal to N1 by N2, that is 1000 by 700. So just putting those values of EB1, we can find that EB2 is 227.74. 274.4 volt EB2. So just putting the value of EB2 in this equation, we found the external resistance that is required, the R, is 2.94 ohm. This is a mathematical problem that we have done. So another is the losses in a DC machine. So there are three types of major losses in a DC machine. One is called the copper loss, copper losses, iron losses or called core or magnetic losses, and another is the mechanical losses. So first we will start with copper losses. So there are two types of copper losses. One is armature copper loss and another is field copper loss. The armature copper loss can be given as Ia square Ra, where Ia is the armature current and Ra is the armature resistance. And the field copper loss is the shunt field copper loss plus series field copper loss. That is Ia square, ISH square, RSH plus ISC square RE, where ISH and ISC are the shunt and series field current, and RSH plus RAC are the shunt and series field resistance. That is the I square R loss. Brush contact is due to the resistance of the brush contact. It is including the armature copper loss. So the iron and the core losses that is given by core or magnetic loss. So these losses is occur in the armature and the field core, and they are generally of two types. One is hysteresis loss and another is called the AD current loss. So hysteresis loss can be given by gauge EM 1.6 F and the AD current loss is KB Bm square F, where Bm is the maximum flux density, F is the frequency of magnetic reversal, and H and K are the constants. So another is called the mechanical losses. So these losses are generally consist of bearing, frictional and windage losses. So in a medium-sized motor, armature copper losses are about 30% to 40% of the full load losses, and field copper losses are about 20% to 30% of total full load losses. Iron losses are about 20% and mechanical losses are about 5 to 10% of the total full load losses. For small motors, mechanical losses are comparable with full load losses, while for larger motors, mechanical losses may be neglected. So, iron losses and the mechanical losses are constant for a particular machine, and they are together known as no load rotational losses. Beside all the above three types of losses, there is an additional loss known as stray load loss. All the losses which do not belong to any of the above categories will be included in this group. In most machines, stray load loss is taken as 1% of the rated output of the machine, and it is generally neglected. So efficiency of a DC machine, that is given by 1 minus losses by output, that is output by input, that is input minus losses by input. So for a generator, the efficiency is 1 minus losses by VIL plus losses, where V is the terminal voltage and IL is the line current and VIL is the output power, but in case of the motor, its efficiency is 1 minus losses by VIL, where VIL is the input power. After multiplying the efficiency into 100, the efficiency can also be expressed in percentage. So let us take a problem in order to understand the losses and the efficiency in a DC machine. So a 480 volt 200 kilowatt shunt motor takes 2.5 ampere while running at no load, taking the armature resistance to be zero point 0.6, field resistance to be 800 ohm, the brass drop 2 volt, find the full load efficiency. So it is given that V equal to 480 volt, P equal to 20 into 10 to the power 3 watt, IL equal to 2.5 ampere, that is no load, and RA equal to 0.6 ohm, and RSH equal to 800 ohm. So what is the value of ISH? ISH equal to VSH by RSH, that is 480 by 800, that is 0.6 ampere. So what is the input power at no load? That is VIL no load, that is 480 VIL into at no load VIL equal to 480 V into IL, that is 480 into 2.5, that is 1200 watt. So field copper loss, that is ISH square plus into RSH, that is 0.64 square into 800, that is 288 watt. So armature current at no load, that is IA equal to IL minus ISH, that is 2.5 into 0.6, that we have already known for a shunt motor, that is 1.9 ampere. So the armature copper loss at no load, that is IA square RA, that is 1.9 whole square into 0.6, that is 2.166 watt. So the brush contact loss, that is 2 into IL, that is bars voltage drop is 2, so 2 into IA, that is 3.8, 2 into 1.9, that is 3.8, but because brass voltage drop is 2 volt. So the core loss plus the frictional losses, that is the 1200, that is the input power, minus 288, that is field copper loss, minus 2.166, that is armature copper loss, minus 3.8, that is 906.034. So under full load condition, the value of line current IL equal to 20 into 10 to the power 3 divided by 480, that is, because it is given, it is a 20 kilowatt, that is the output power of the motor is 20 kilowatt. All these data are given on the output basis. So 20 into 10 to the power 3 by 480, that is 41.67 ampere. So IA at the full load, that is ISH, will remain same. So IL minus ISH, that is 41.67 minus 0.6, that is 41.07, that is the value that we have obtained. So again, we can calculate the armature copper loss, that is IA square at full load into 0.6, that is 1012.05 watt. Total losses, that is 101, that is the armature copper loss, plus 288, that is coming from the field copper loss, plus 906.034, that is core and the frictional losses, plus 2 into 41.047, because now the armature current is 41.0747 at full load, and 2 is the brush voltage drop. So here's the full load efficiency, that is input minus loss by input, that is 1 minus input by losses, that is 1 minus, this is the total losses by total input, that is 2000, that is 220000, is 20,000. So in the percentage, after multiplying the output, that is 0.8855 into 100, it is 88.55%. So we now able to calculate the efficiency and solve that problem. So another problem is the DC motor starting. So the armature current of a DC motor can be given as, during the starting, IA is equal to V minus EB by RA. So IA, that is depends upon EB and RA, where V is kept constant. When the motor was switched on, the armature is in a stationary condition, so there is no back EMF conception, so EB equal to 0, as EB is directly proportional to speed that we have already seen. So the starting current, as the EB became 0, so the starting value of the current is IA is equal to V minus RA. Since the armature resistance of a motor is very small, generally less than 1 ohm, therefore the starting armature current IAS would be very large. For example, if a motor with armature resistance 0.2 ohm is connected directly to the 230 volt supply, the IA is equal to V by RA, that is 230 by 0.1, is the starting current is 1150 ampere. This large amount of current could damage the brushes, commutators, or winding. Also, it may damage the supply installation because as the EV becomes zero at the starting current is very large for DC motor. As the motor speed increases, the back EMF increases, and the difference between these two, that is V minus EV, that goes on decreasing. This result in the gradual decrease of IAS until the motor attains its stable rated speed and the corresponding back EMF. Under this condition, the armature current reaches its desired rated value. Thus, it is found that the back EMF helps the armature resistance in limiting the current that is through the armature. In the starting, as the current is very large, at the time the starting of the DC motor, it's a very small motor and extra resistance must be connected in series with the armature. This would limit the initial current to a safe value until the motor has built up the stable speed and back EMF EB. This external resistance is basically known as starter resistance. The series resistance is divided into sections which are cut out one by one as the speed of the motor increases and the back EMF builds up. When the speed of the motor attains its normal value, the external resistance or external starting resistance, which is known as starter resistance, is completely cut out. So the 3-point starter, this is a 3-point starter for DC shunt motor. In a 3-point starter that is connected to the DC shunt motor, as given in this figure, is the DC shunt motor. And as the three terminals that we have, that is L, A, and F, are available from the starter, and it is called a 3-point starter. The terminal L is connected to the supplies terminal, the mains. A to the armature, A is generally connected to the armature, and A is clearly seen that is connected to the armature here, and F is connected to the field winding or the field terminals. When the motor is at rest, the starter S is kept on off position. When the motor is raised, the starter L is in the off position, in this position. By a spring, with the help of a spring, it is held at that off position, that is starter. The motor that is disconnected from the supply is clearly seen. When the motor is going to be started, the handle moves to the one position. As a result, the handle that is moved to the one position, the shunt field and the holding coil get supplied and they got energized. And the entire starting resistance, that's connected in series with the armature resistance. As a result, the entire resistance is now connected in series with the armature resistance. When it's coming to that position, look at that armature resistance, this one. This is the armature resistance, and the entire series resistance now gradually connected to the armature resistance. As the armature starts rotating and the handle is gradually moved through all the stars until it starts the holding magnet. The holding magnet is called no voltage release, or this is until it touch. This is the gradual start, and until it come to this S, that is until come to the no voltage release or low voltage release coil. In case of the power failure, if the holding coil get de-energized and the handle is again brought to the off position, means it is moving, cutting all those resistance gradually, it is moving to the no voltage release, and as the power failure, it is come back as this coil get de-energized and it cannot be able to hold it, and it is come back to its off position, that is starter handle is by an spring action that is clearly seen here. Again, if by any chance shunt field winding gets open circuited, the holding magnet get de-energized if the shunt field magnet get open circuited, and the starter handle return to the off position again. This is the another coil that is called the overload release coil. This one, which protects the motor against excessive load. When the armature current exceeds a particular value, the overload release coil attracts the soft iron and armature, and it is attract the soft iron armature, and as a result the no volt release coil get short circuited. The stator is pulled back to its off position by spring action as the holding coil get de-energized or demagnetized, and the motor trans automatically switched off. This is a 3-point starter for a DC motor. And the reversal of the rotation of DC motor, the direction of the rotation of a DC motor can be reversed by reversing the connection of either the field winding or the armature, but not both. It is to be noted that in order to reverse the direction of rotation of a compound motor, the reversal of field connections involves both shunt and series windings. So the application of the DC machine, DC generator application, DC generators are now being used in dynamometers for measuring torque, etc. For welding purpose as control type of DC generator for closed loop system, permanent magnet DC generators, etc. Separately excited DC generators are used to serve an excitation source for large alternators in power generating station, to serve as control generator in were Leonard system of speed control, and to serve as auxiliary and emergency power supplies. Motor application: when constant speed services at low speed is required in industry, shunt motors are used. When driven load requires a wide range of speed control, DC shunt motor used, that is in lathe. Since series motors have high starting torque, it is the best suited for driving hoists, trains, etc. They are widely used in all types of electric vehicles, electric trains, streetcars, battery powered, portable tools, etc. Compound motors are used in rolling mill drive, punching press, planing, or milling machine. When the supply voltage across the motor terminals is likely to vary considerably, such as in traction motors, compound motors are preferred. As separately excited DC motors are easily adaptable to a wide range of speed and torque control. In high power application, these are widely used in Steel and aluminum rolling mills were Leonard method of speed control in low power application. Separately excited DC motors find use a control motor. Thank you.